in today's session, we are going to look into the design of another different type of footing, which is called as a sloped footing. So we can also call this sloped footing as a trapezoidal footing as well. We can call either design of sloped footing or trapezoidal footing. The design procedure remains same. Nothing much change will be there with between the sloped and trapezoidal footing. Okay. So first let us understand what is the problem statement, and then I'll show you how to do the design process of sloped footing. So the problem statement goes in this way: design a footing for a rectangular column of size 300 by 600 mm. This is the column size, which is carrying a service load of 166.67 kilonewtons. So this is the amount of load that is being carried by the column. Okay, and the safe bearing capacity of the soil is 200 kilonewtons per square meter. Grade of concrete is M25 and grade of steel is Fe415. So that's the details that is provided in the question. And here in this problem statement, the dead loads and live loads are not provided directly. The total service load is provided. Okay, the total load that is provided, that is being carried by the column, is provided here. So you don't need to do any kind of dead load calculation or live load calculation. Just for a difference of thing, I just made it in this way. Okay, right. So first thing is, however, we have to calculate the self weight of the footing. So let me keep the heading as loads. Okay. So in the loads, what we have to calculate is, initially when the dead loads and live loads are given, we are going to add those dead loads and then we'll get the total load. But here there is no dead load. So let us make it as a total service load equals to, it is already given in the question, that is 166.67 kilonewtons. That's the amount of service load. And how to find out the self weight of the footing? So self weight of footing equals to, self weight of footing equals to 10% of column load. 10% of column load. So what is 10% of column load? So how much is the column load? Column load is 166.67. See, again, I'm not going into the details of each and every step because we have already discussed those minute details in the previous discussions, right? So that's why I'm directly jumping into the steps, right? So if you get any doubts at any point of time, you can unmute and ask the doubts, right? So therefore, the 10% of 166 will become 166.67 kilonewtons. So this is the self weight of the footing. So from this, we can calculate the total load, okay, that equals to 166.67 plus 166.67. So that's the total load, which will be 1833.34 kilonewtons. So this is the total load that is coming onto the member, that is footing. So based on this load, we have to find out the area of the footing. So how will you find out the area of the footing? So the area of footing can be found out based on the load categories. So let me write that. So area of footing. So how to find out the area of load, area of footing? Footing area can be found out by using the total load and also the SBC of the soil. So we can say it as required area of footing equals to, the required area of footing equals to total load, that is 1833.34 divided by SBC of soil. What is SBC of soil? It is already given in the problem, which is 200. So 1833.34 divided by 200 will give us the value of 9.1667 square meters. So this is the total area of footing. Now, based upon this area, we have to find out the length and width of the footing. Okay, based upon this area, we have to find out length and width of the footing. But if you see the problem statement here, I was mentioning in the very first session of design of rectangular footings, if the column size is, or if the column shape is a square column, then we have to design square footing. If the column is of rectangular shape, then we have to design rectangular footing. So by that thumb rule, what we can say here is it's a rectangular column. So since it's a rectangular column, we have to design the rectangular footing only. Okay, we have to design rectangular footing only. So let us find out the dimensions of length and width of the footing. So we can write this as length of the footing into width of the footing equals to 9.1667. So this is the value. Okay, length and width. Length is length and width of the footings we have to find out. This is basically the area. Okay, 9.1667 is basically the area. So let me call this as equation 1. Okay, right. So now what we have to do is we have to find out length and width of the footing. Now, how to find out the length and width of the footing of a rectangular footing? So we know one rule, or we know one condition, which is, suppose if you have a rectangular, okay, if you have a rectangular footing inside which you have a rectangular column. Okay, you have the rectangular column. So how will you place the rectangular column? So the rectangular column has to be placed in such a way that from any direction, okay, from whichever side you take, the projection should remain same. Okay, that is, the value of x should remain same on all the four sides. That is what you have to follow when you are positioning the columns. Okay, the value of x should remain same on all the sides. Now the question is how to find out this value of x. Okay, how to find out this value of x. So we know the length of the footing, that is LF. Okay, we can say it as length of the footing here, and the width of the footing, which is B suffix F. Okay, and the rectangular column dimension. So we can call this as small a. Okay, this length as small a. Just a second. So this length as small a, the longer side, and the shorter side is small b. Okay, so the width of the footing or the length of the square column, I'm taking it as a, and the width of the rectangular footing, I'm calling it as b. Okay, the length of the rectangular footing is a, and the width of the rectangular footing is b. Right. So from this, we can get the values of LF and BF. So how to get the values of LF plus BF? So LF equals to, that is the length of the footing. LF equals to, okay. So how to get the value of LF? This is the total length. Okay, LF length is this one. So this is the total length of LF, right? So how to get the value of LF? X plus A plus X. So if you add all these things, okay, so if you add this X and then this length of the column and X, so X plus A plus X, that is, you can make it as A plus 2X. Okay, length of the footing equals to A plus 2 times of X. Similarly, width of the footing, BF equals to B plus 2X. Okay, B plus 2X. So from top, you have to consider. So this X, okay, this one plus B plus X. So X plus B plus X, that is B plus 2X. So that's how we can get the value of LF and BF. But here, what we should know is we should know the value of X. Okay, we should know the value of X. So substitute the LF and BF values in the equation 1. Okay, substitute LF and BF values in equation 1. So LF is A plus 2 times of X into BF is B plus 2 times of X equals to 9.1667. Okay, that's the value. So if you solve this equation, it will become a quadratic equation. Then you are going to get the value of X as 1.29 meters. That's the value of X. Now, from this value, we can get the values of length of footing and width of the footing. So let us write that. So LF equals to A. What is A? A is length of the column. So what is length of the column? The larger dimension will become the length and the smaller dimension will become the width of the column. So from this, the length of the column is 600 mm. So A plus 2x. A is 0.6, that is 600 mm, plus 2 times of X. What is X value? 1.29 meters. So from this, we can get the value of length of the footing as 3.18 meters. So approximately what I'll do is I'll make it as 3.2 meters. Right. And then the next value is a BF, that is width of the footing. So width of the footing formula is B plus 2x. What is the value of B? The smaller dimension of column. What is smaller dimension of column? 300 mm. So the value of B will become 0.3 plus 2 times of x. So 2 times of x is 1.29 meters. So that equals to 2.88 meters. So that equals to 2.9 meters. So I'm just rounding it off to 2.9. So that's how we'll get the length and width of the footing. So let us find out the provided area of footing. Okay, provided area of footing equals to 3.2, that is length of the footing, into width of the footing, that is 2.9 meters. So that equals to 9.28 square meters. So how much we have to provide? We have to provide 9.1667. But how much we have provided? It is 9.28 square meter. So there won't be any problem with respect to the area. Okay, right. The next one is we have to find out the upward soil pressure. Okay, we have to find out the upward soil pressure. So how to find out the upward soil pressure? So upward soil pressure. So how to find out the upward soil pressure? Upward soil pressure can be found out by using the formula W equals to, that's the formula, W equals to, so upward soil pressure is represented with a small w. W equals to the total load. Okay, the total load is 166, sorry, not this one. Yeah, this one. Total service load 166.67 divided by 166.67 divided by area of the footing, that is provided area, which is 9.28. 9.28. So therefore, the net upward soil pressure will become 179.59 kilonewtons per square meter. Okay, this is the net upward soil pressure, right? So from this net upward soil pressure, the next parameters we have to find out. What is the next step? The next step is depth required for flexural criteria. So we have to find out the depth based on flexural criteria and also based on shear criteria as well. Right. So before doing this one, we have to remember a couple of points while designing the rectangular sloped footing or trapezoidal footing, you can say. Let me delete this diagram. Yeah. So while designing a trapezoidal footing or sloped footing, we need to remember a couple of things. So let me write that. While designing So while designing the sloped or trapezoidal footing, while designing sloped or trapezoidal footing, we have to consider two important parameters. Two important parameters. So what are they? So the first parameter is the projection. The projection from face of the column on all sides is taken as 75 mm. Okay, is taken as 75 mm. So I'll represent this with small k. Some notation I'm giving here. That's it. That's the first thing. And the next one is depth at edge of footing is taken as or is provided as 230 mm. So I'll call this one as capital D2. I'll explain what are these values. I'll explain now. Right. So usually how the sloped footing will be lying? Sloped footing will be like this. Let me just draw the diagram. All right. So if you take a sloped footing, it goes in this way. So this is how sloped footing will looks like. Okay. So yeah. So this is how the sloped footing looks like. So what I am telling here is the parameters, the two important things. What is the first one? Projection from face of the column on all sides is taken as 75 mm. So what is the projection from face of the column? The projection from face of the column is nothing but this one. This is the projection from face of the column on all sides. So this projection should be 75 mm. Okay, that is the as per the code versions. So 75 mm projection has to be given. That's the first point. And the second point is depth at edge of the footing. Okay, depth at edge of the footing is taken as 230 mm. So what is depth at edge of the footing? Depth at edge of the footing is nothing but this one. This is the depth at edge of the footing. Okay, this is the depth at edge of the footing. So this is taken as 230 mm. So usually we'll provide up to 250 mm, but 230 mm is generally considered in the real-time practice. Okay, this one I'm calling it as D2. Okay, this one I'm calling it as D2. And this height, okay, whatever the remaining distance from here. So this height, I'll call it as D1. We have to do some calculations here. So I'm just giving you a glimpse of what we are going to do. Right. So these are the 2 points that we need to remember. So the first one is the projection from face of the column. So this is the column face. Projection from face of the column on all sides is taken as 75 mm, and the depth at edge of the footing is taken as 230 mm. Right. So based on this criteria, we have to find out the depth required for flexural criteria and depth required for shear criteria. I hope this diagram is clear. Right. So now let us do the calculations. So let me write that step. Just give me a second. Yeah. So the depth required for flexural criteria. Flexural criteria. So the depth required for flexural criteria. Now we know that moment has to be calculated. Okay, whenever we are calculating the moment has to be calculated. Moment has to be calculated along the column face. Okay, along the column face, along length and width of footing. So we have to find out the moment along the length of the footing and along the width of the footing. That we have seen ML and MB, right? We have done the same calculation while designing the rectangular footing as well, right? So first let us calculate moment along the length of the footing. Okay, moment along the length of the footing. So when you are calculating the moment along length of the footing, we know one condition, that is we have to consider, okay, we have to consider the width of footing. Okay, when you are calculating the moment along the length, we have to consider the width of the footing. When you are calculating moment along width of the footing, we have to consider length of the footing. I'll tell you that. So this we know already. We have talked about this one. So I'll just call it as ML, that is moment along length of the footing, that equals to, right, moment along length of the footing equals to upward soil pressure. Okay, that is 179.59. Upward soil pressure is 179.59 into, we have to consider width of the footing. What is width of the footing? The width of the footing is 2.9 meters. So into 2.9 meters multiplied by, we need to have one calculation here. What is that calculation? Suppose if you take the column, or if you take the rectangular footing, let me draw that one. Inside which we have a rectangular footing, a rectangular column, right? So here what we have to do is what is set in the problem statement. I mean, here what I have mentioned, moment has to be calculated along the column face. Okay, moment has to be calculated along the column face. So how many column faces we have? Two column faces we have. What are they? The first one is this one. Okay, this is first column face, and the second column face is this one. Okay, along length we have one column face, and along width we have one column face. So here, initially, suppose, let's say I want to find out this span. So how to get this span? So we know the total length of the footing, that is LF value, and we also know the length of the column, that is A. Okay, so therefore this length will become LF, that is length of the footing, minus A divided by 2. So when you solve this one, you are going to get this particular length. Okay, you're going to get this particular length. Similarly, this is along length. Okay, first let us finish out with the length factor. So into LF minus A. What is LF? Length of the footing. What is length of the footing? Length of the footing is 3.2 meters. So 3.2 minus A. What is A? Length of the column. What is length of the column? So you can see 600 mm. So that will be 0.6. Okay, 0.6 divided by 2. Okay, 3.2 minus 0.6 divided by 2, you will be getting the moment value along the length. Okay, that will become square. Okay, L square by T. Right. So that will be moment value will become 440.11 kilonewtons meter. Okay, 440.11 kilonewtons meter. That is moment along length. But we need to work for the ultimate moment or factored moment. So I will call it as MLU. So ultimate moment or factored moment equals to 440. That is 1.5 times of 440.11. So this value will be 660.15. 660.15 kilonewtons meter. So that's the moment along length value. Now similarly, we have to calculate moment along width as well. Okay, moment along width as well. So how to get the moment along width? So moment along width equals to upward soil pressure, that is 179.59 into, so when you are calculating the moment along width, okay, let me write this one. When you are calculating moment along width of the footing, we have to consider the length of the footing. Let me write. We have to consider the length of footing. Right. So MB equals to upward soil pressure into the length of a footing. What is length of the footing? Length of the footing is 3 point something, 3.2. Yeah. So length of the footing is 3.2 into, okay, into this value. So along width we are calculating. So what will become this value? So we have to find out this value. Okay, along width. So how to get this value? So this value will be, we know the width of the footing, that is taken as a BF. Okay, that is width of the footing. And this side of the column we know that is small b. Okay, so BF minus B divided by 2. Okay, that is this span. BF minus B divided by 2. So same formula we have to apply here. What is BF? BF is width of the footing. So what is width of the footing? Width of the footing is 2.9 minus, what is this side of the column? So it is something like 300 mm. So 0.3. Okay, 0.3 divided by 2 whole square. So from this, we can get the moment along width value. So therefore, moment along width equals to 485.61 kilonewtons meter. Okay, 485.61 kilonewtons meter. So now we need to get the factored moment, that is MBU equals to moment along width direction. MBU equals to 1.5 times of 485. Okay, 485.61. That equals to 728.42 kilonewtons meter. So this is the moment along length value and moment along width value. So based on this moment calculation, what we have to do next is we have to find out the depth required for flexural criteria. Okay, we have to find out the depth required. So how to get the depth required value? It is based on the grade of steel. Okay, it is based on grade of steel. So how to get that? So depth required equals to right. If you want to find the depth, mu equals to 0.138 FCK BD square. That's the formula. Okay, 0.138 FCK BD square. Just a second. Yes. So from this, we are going to calculate the depth value. Right. So now here, what is the value of mu? Mu is the maximum moment, but we have two moments here. One is this one and the other one is this one. So among these two, whichever is the highest value. Just a second. Just give me a second. So here, so depth required, we have to calculate along two directions. Depth required, one criteria we have to find out. First, let me talk about that one. 0.138 FCK BD square. So here, what we have to do is first we have to find out the depth along two directions. So depth required along length of footing. Okay, this is one criteria. And the second one is depth required along width of footing. Okay, depth required along length of footing, mu equals to 0.138 FCK BD square. Okay, so here what is mu? Mu is moment value, okay, the value of moment along the length direction. What is the value of moment along length direction? 660.15. So 660.15 into 10 power 6. That equals to, okay, that is mu equals to 0.138, 0.138. FCK is grade of concrete, which is given as 20, and the B value. This is something typical here. So how to find out the value of B? Okay, how to get the value of B? So in order to get the value of B, we need to understand one particular figure here. Let me draw that. So here, if you see the footing or sloped footing from top view, it looks something like this. Let me show you that. Okay, this is the column. And when you see it from the top, since it's a sloped footing, it looks like this. I hope you are getting the diagram. So when you're seeing from the top, it looks something like this. Now here we have the column portion. Okay, we have the let me write that. So we have the column portion here. Okay, we have the column portion here, right? So here we know the value of x, that is projection value. What is projection value? The projection is 75 mm. If I'm not wrong, let me just have a cross check. So the projection from face of the column, yeah. So projection from face of the column on all sides is taken as 75 mm. So we know the projection value is 75 mm. So let me write that projection value. So this is 75 mm. So on all sides, the value will be 75 mm. All right. So this is the projection value. Now what we have to find out is we have to find out width of a footing. Okay, we have to find out the width of footing at the top. Top portion is this one. Okay, remember this. Top portion is this one. So we need to consider the width of only this portion. Okay, we need to consider the width of only this portion. Why? Because we have two different widths. This is one width, that is sloped width, and this is another width, the original width. Okay, so for two different widths are there, so we'll get two different depths, right? So first we have to find out the width of this footing. Okay, we have to find out the width of this particular area. So this B we have to find out. So let me call this as B, right? So now resisting width we can call this as. So resisting width at top of footing. So let me write that here itself. Right. So resisting width at top of footing B equals to, okay, resisting width at top of footing B equals to. So this value we have to find out. What is the size of the column or B value of the column, small b of the column? 0.3, that is 300 mm. That's the size of the column along the width, plus on top it is 75 mm and at bottom also it is 75 mm. So we can make it in this way. So 75 plus width of the column plus 75 at the bottom. So this value will become, so it is 150, that equals to 450 mm. So 450 mm, that is the resisting width at top of footing. So here the value of B will become 450. That's how the value of B gets changed. Okay, that's the difference between a typical rectangular footing and a rectangular sloped footing. This is the change. Okay, 0.138 FCK BD square. So D value we don't know, so let us keep as it is. So if you solve this equation, you're going to get the depth of the footing, okay, equals to 652.07 mm. So this is the depth that is required along the length of a footing. Okay, along the length of footing, this is the depth that we need. Now, similarly, we have to find out the depth value along width of a footing as well. Okay, the depth value along width of the footing as well. So let me write that. So depth required along width of a footing. Same formula, 0.138 FCK BD square. But the value of B will get changed. Okay, the value of B will get changed. So how to go with this? So what is this side of the column? Okay, what is this side of the column? This side of the column is 600 mm. So 75 plus 600 plus 75. Okay, 75 plus 600, that is length of the column, plus 75. So that will become 750 mm. Okay, so if you solve this equation, you are going to get the value. And similarly, moment along width direction. What is moment along width direction? 728. So we have to change this value as well. 728 point, okay, 728.42. So this is the value. So from this, the depth value gets changed, which will be 530.58 mm. So this is the depth required along the width of the footing. Now here, if you observe, we are getting two depth value. One is 652 mm and the other one is 530 mm. So which one we have to consider? So among these two, whichever is the highest value, that you have to consider as the depth required. Okay, along these two, whichever is the highest value, that you have to consider as the depth required for the footing. Right. So therefore, depth required. Therefore, depth required for the footing equals to highest of depth along length and width of footing. Okay, so among these two, whichever is the highest values, that we have to consider. So which is the highest value? Depth along length is highest value, that is 652 mm, 652.07 mm. So we cannot provide exactly 652.07. So we can round off that value to 900 or 950 or 1800. That's up to you. So you try to adopt the higher value so that the limits will be falling within the conditions itself. So what I'll do is I'll consider the overall depth. Okay, therefore provide overall depth of footing. Overall depth of the footing, capital D, equals to 950 mm. That's the overall depth of the footing. Okay, so from this we can get the clear cover. So assume clear cover or cover equals to 50 mm and diameter of bar equals to 16 mm. This is what we have been considered. So from this we can get the depth provided. The depth provided equals to overall depth, that is 950 mm, minus cover, that is 50 mm, minus diameter of bar divided by 2. So if you solve this one, this is the depth that we have to provide. Okay, the effective depth that we have to provide, which is 892 mm. So based on this depth condition, we have to find out the reinforcement. That's the next step. Okay, I hope it is clear up to here. If you have any doubts, you can unmute and ask the doubts. I'll just, I'll wait for your doubts if you have any, so that I'll clarify your doubts. Okay, so I'll consider you don't have any doubts. Right. So the next step is a design for reinforcement. Now here, the reinforcement has to be provided along the length of the footing and also along the width of the footing. So that's again another criteria. So reinforcement along length of the footing. So first we'll find out along length and then we'll find out reinforcement along width of the footing. So first let us find out the reinforcement value along length and then we'll find out the value along width. Right. So how to get the reinforcement value? So we have the equation, that is AST equals to, let me just check that equation. Yeah, this. So AST equals to 0.5 FCK by Fy. Yeah, this one. So from this equation, we have to find out the AST value, that is area of steel value. So here, since we are finding out the reinforcement along the length direction, the value of mu will be the moment along length direction. So what is moment along length direction? It is 660.15. Okay, moment along length equals to 660.15 into 10 power 6 into 10 power 6. Right. So that is moment along length direction. And then the value of B. So B equals to, what is B? B is width at the top of footing. Okay, B is width at the top of footing. What is width at top of footing? So we have found out that. Just give me a second. Where is that? Is that? Yeah. So resisting width at the top of footing. Yeah. So resisting width at top of footing is 450 mm. So therefore, the value of B will become 450 mm. So B equals to 450 mm, and the effective depth D equals to 892 mm. So we have just solved it here. So D equals to 892 mm, and the value of FCK, that is grade of concrete, is 20, and Fi value is 415. Right. So from this we can get the value of AST, that is area of steel. So therefore, area of steel equals to 2262.52 mm square. That's the area of steel. So you can call this as the design requirement. Design requirement. Right. So this is the AST value. Now let us find out the minimum reinforcement value. So minimum reinforcement, AST minimum equals to 0.12% into B, that is 450, into overall depth. What is over? Sorry, not B is not that one. B is width of the footing. So what is width of the footing? It is something like 2.9. Yeah. So width of the footing is 2.9. So minimum reinforcement 2900 B into overall depth. What is overall depth? We have assumed it as 950 mm. Okay, here. So therefore, B equals to 950. So 0.12% BD. Okay, so that equals to, what will be the value? 3306 mm square. Okay, 3306 mm square. So here we have to provide the 16 mm diameter bars. So provide 16 mm diameter bars. So area of one bar of 16 mm diameter, area of one bar of 16 mm diameter equals to pi by 4 into d square, where d is the 16 value, which will become 201.06 mm square. Okay. Now let us find out the spacing value. So spacing required equals to area of one bar, that is 201.06, divided by the total area of reinforcement, which is 3306. See, you should not take this value. Why? Minimum you have to provide this much. Design requirement is this much, but you have to always provide the minimum reinforcement value. So among these two values, whichever is the highest value, that you have to provide. So don't always provide directly this one. You have to always cross check whether design requirement value is less than minimum reinforcement or greater than minimum reinforcement. If the design requirement value is less than the minimum reinforcement value, then you have to provide minimum reinforcement value only. If the design requirement value is greater than the minimum reinforcement value, then you have to provide design reinforcement value, design requirement value only. That's the most important thing. So don't confuse that. So spacing required equals to area of one bar of 16 mm diameter by total area into the width of the footing. What is width of the footing? Width of the footing is 2900. So therefore, the spacing value will be 176.36 mm. So we can round off this value to 125 mm or 150, whatever. So I'll just round it off to 125 mm. So therefore, provided spacing, okay, provide a spacing of 125 mm center to center. So from this, area of steel provided, AST provided, PROV, I'll just make this. So AST provided equals to, so how to find out this AST provided value? Right. So AST provided equals to area of one steel bar, that is 201.06, divided by spacing, that is 125, into width of the footing, that is 2900. So from this, we are going to get the area of steel that has to be provided along the width direction. Okay, along the, sorry, not width, length direction. Correct. Similarly, we have to do the calculation of reinforcement along the width of the footing. Okay, reinforcement along width of the footing. So I'll just copy this entire one and then I'll make the changes just to save the time. So let me delete these ones. Just give me a second. Right. So AST formula we know. So first we are finding out the reinforcement along width of the footing. So here mu value will get changed. That is moment along width of the footing. So what is moment along width of the footing? 728.42. So 728.42 into 10 power 6 into B. What is B? B is width of the factor called footing. So what is width, resisting width at top of footing? This is along, yeah, this one. Depth required, yeah, resisting width at top of footing along depth direction, which is 750 mm. So B value will become 750 mm and the effective depth will not change. It is 892, FCK is 20, Fi is 415. So therefore, area of steel will get changed, which will be 2406.62 mm square. So minimum reinforcement condition is 0.12% length of the footing. So what is length of the footing? 3.2 meters. So that will be 3200 into D. So which will be the overall depth is same, that is 950 mm. So therefore, the area of steel will become 3648 mm square. So similarly, again, we have to provide 16 mm diameter parts and the area of one bar remains same. So spacing required equals to 201.06 divided by 3648. 3648 into the length, that will be 3200, which will be equals to 176.32. I think the value remains same. Okay, so 176.32. So I'm just rounding it off to 125 mm. So therefore, AST provided equals to area of one bar by spacing into the length. So therefore, length value will be 3200. So if you solve this one, you are going to get the AST provided along the width of the footing as 5147.14. So this is the area of steel that you have to provide along the width direction. Okay, this is along width direction. And this is the area of steel that you have to provide along length direction. That's the calculation. Right. So now we have to look for the shear calculation. Okay, shear force calculation. So shear force calculation is little complex here because we cannot use the same formula what we have been using for the shear force calculation. So I'll show you that which one we have to use and what has to be adopted. Give me a second. Yeah. So check for one-way shear. Okay, check for one-way shear. So how to check one-way shear? So in order to check one-way shear, since here the depth of the footing is
Sir, you're on mute, I guess.
Oh, right. So am I clear now? I mean, am I audible now?
Yes, sir.
So till now, you didn't heard anything?
No, just 1 minute back. That's it.
Okay, fine, fine. Okay, right. So here you can see the beams of varying depth, which is given as annexure B. You can see annexure B, clause 5.1.1. So here, what they are telling is, in the case of beams of varying depth, the equation shall be modified. That is shear equation. Tau V is shear force. So shear equation can be modified as V plus or minus m tan beta divided by D divided by B into D. So from this formula, we have to find out the shear force or one-way shear. We have to check whether tau V is less than tau C or not based on this particular equation. So let me just copy this equation. Let me just take a snapshot of this one. And let me provide it here. Yeah. So based using this formula, we have to calculate the tau V value. Right. So, but before calculating the tau V value, it is something complex here with respect to the value of D. Okay, with respect to the value of D. So let us find out what is the value of D here. So for that, what I'll do is I'll show you one particular image. Let me just show you that. I just have that again. Just give me a second. I'm just checking whether this is the right diagram or not. Yeah, this could be the right one. Just give me a second. Let me copy this one and paste it here. Yeah. So understanding this diagram is very, very much important. So here I have given all the values, so it will be very confusing for you. So I'll explain it from one by one. So we know the overall depth of the footing. The overall depth of the footing is 950 mm. That we know, right? And then we also know the depth at edge of the footing. Okay, the depth at edge of the footing is 230 mm. Now, if you want to find out this depth, okay, if you want to find out this depth, so 950 minus 230, which will be 720 mm. Okay, 950 minus 230 will be 720 mm. So up to here, you make sure of this one. So this depth, overall depth is 950 mm, and the depth at edge of the footing is 230 mm. So in order to get this value, okay, 950 minus 230. 950 minus 230 will give us the depth of the sloped size of footing or sloped side of footing. Right. So 950 minus 230. Now, the next thing is the critical section. So we know that in one-way shear calculation, the critical section is always considered at a distance D from face of the column. So here, the critical section, what I am considering is this is my critical section. Okay, this part is my critical section. So this is the critical section value. So I'm considering that critical section will be lying at a distance D from face of the column. This is the face of the column, and it is lying at a distance D from face of the column. So this distance. So here we have to find out the critical section area value, that is a D value. So critical section D value is important to find out now. And the other parameter is here you can see D and D dash is given. What is D and D dash? D is nothing but from here, from top of the footing or from top of the sloped footing to center of the reinforcement bar, which is provided at the bottom. So here the red color one is the reinforcement bar. Okay, from top of the sloped footing to the center of the reinforcement bar, I'm calling it as effective depth. And similarly, here you can see there is one more factor which is called this one. So this is the one-way shear calculation. Okay, D value. Okay, this is the one-way shear calculation D value. So critical section will be lying at a distance d from face of the column. So this value we have to find out. Okay, this value we have to find out. So here what I have done is from here, okay, from this critical portion part to the center of the reinforcement bar, I'm considering it as d dash. Okay, I'm considering it as d dash. So let us solve these ones first, and then I'll show you. So how to get the value of d dash, and then how to get the value of y dash, and then how to get the value of d along with the critical section d value. Right. So let's consider the critical section at a distance d from face of the column. Let me write that. So let's consider the critical section for one-way shear will be at a distance d from face of the column on all sides. So this is how we are going to get the critical section. So here the critical section d equals to, we have to find this value. This value we have to find out. Okay, this value we have to find out. So how will you find out? So we know the overall depth, that is 950 mm, and we know the diameter of the steel bar, which is 16 mm diameter bar. Okay, we know the overall depth, that is 950 mm. So if you solve this one, so let me just open my calculator. So the overall depth is 950 mm minus the diameter of the steel bar is 16. So it is considered from half of the distance. So 16 by 2 will become 8. So that will be 942 mm. Okay, that will be 942 mm, this distance. But again, still there is some calculation that needs to be understood here. Let me just write that part. Right. So this d value we have to find out. So how to get this d value? So this d value will become, so I'll write it here. Oh, sorry. Right. So this d equals to, overall depth is 950 mm. Okay, 950 minus the clear cover value. What is clear cover? 50 mm minus the diameter of bar. What is diameter of bar? 16 mm divided by 2, half of the diameter of bar. So 950 minus 50 minus 16 by 2. So if you solve this one, 950 minus 50 minus 16 by 2 is 8, which will be 892 mm. Okay, 892 mm. So that's how this d value has to be found out. So what is this value? This is this one. Okay, critical section will be lying at a distance d from face of the column. So the distance d value is 892 mm. I hope it is clear. So let me write that. Make sure of understanding this one. So critical section d equals to 892 mm. So how we are getting 892 mm? So overall depth, that is 750 minus clear cover, that is 50 minus diameter of bar divided by 2, which will be 892 mm. So that's the critical section distance d. Now similarly, we have to find out another value, that is depth at edge of projection from face of the column. What is depth at edge of projection from face of the column? Here. So this one, this distance. Depth at edge from face of the column. So from face of the column is this one. Okay. So from here to here, what is the depth? That is 720 mm. Okay, that is 720 mm. So how we are getting this 720 mm? So 950 minus 230. Overall depth minus edge at face of the column. That is 950 minus 230. That equals to 720 mm. That is edge of projection depth from face of the column. And then total depth we know. So total depth, capital D, equals to 950 mm. 950 mm. And then edge depth equals to 230 mm. Right. So these are something. And the other thing is, we need to find out the height of y dash value. This one, the height of y dash value. So how to get the height of y dash value? So in order to get this one, we have to go with this equation. That is not equation, calculation again. So y dash equals to, so how to get this y dash depth value? So we know this depth, that is 720 mm. So 720 minus, sorry, not minus, 720 times of, just give me a second. 720 is this particular depth into this length we have to find out. Let me just check that length, which is 408 mm. Let me have this calculation for 408. So it will be like, just give me a second. I'm just checking with this calculation. I have written 408. $720 is this one. Okay, that's fine. And then this distance is 408, but let me check what is this distance. So the overall length of the footing is 3.2, that is 3200 minus D, that is 720. Let me have a cross check. 3200 minus D value is 720 is 2.48. Just give me a second. I'm just checking how this 408 value I have written. So we have some calculation must be done. If anybody gets an idea before me, like you can also let me know. 408. It is like center of gravity of the section. So let us find out the center of gravity of the section. Let me just calculate on paper and then I'll let you know. Yeah, it's a center of gravity calculation only. I'll do one thing. So I'll start this one. I mean, I'll do it from here from the next session because we have to find out the center of gravity. So all these three values we have to find out: 408, 1300, and 1225. So it takes at least some 15-20 minutes more. So I'll end the session for up to here. In the next session, what I'll do is I'll show you how to calculate this 408, 133, 1300, and 1225 values. Okay, from here we'll solve and then we'll get the values of tau v and then we'll check whether tau v is less than tau c or not. And then we'll find out the two-way shear check also. Only one-way shear and two-way shear is pending. Apart from that, nothing else. Okay, right. So that's from my end for this particular session. If you have any doubts, you can unmute and ask the doubts. Thank you.